now we want to solve exponential equations. Why would I call that an exponential equation?
There's a plus.
Because there's exponents, but what? There's what in the exponent?
The number.
Variables.
There are variables in the exponent. So this means it's exponential since there's a variable in the exponent. Okay. If you'll recall, the key to this is to make them have common bases. That's the kicker to these. That is an x plus 3, yeah. So, you have to ask yourself, what is a base number in common to 9 and 27?
3.
They both can be 3 to a power. So, we're going to change 9 into 3 squared, and we're going to change 27 into 3 to the third, yes. Okay, so we change them both to 3. They have to have the same base. Now, you need them both written up top as 3 to a power.
Did you change the exponent on the outside?
Oh, whoops, sorry. I thought it was a 4. I didn't look. It's a 3.
Is that 3 squared?
Is that 3 squared where? That's 27 is 3 cubed.
I was really confused as why you changed it.
Sorry, no, I just miscopied. I must have looked at this 4. Okay, so it's the same thing. Plus 3. That's a 4, yes. 4. Okay. So now I need this up as 3 to a power. So if it's on the bottom, it's negative 2x. I can bring it up. Then, how did we write a root as a power? Yes, that would be 3/4. 3/4. Leave the outside out there.
True that.
Okay. Once you have the bases exactly the same, everything's up top. If the bases are the same, then we know the exponents have to be equal, don't we?
These are so hard.
So you can just drop the 3's out of there, and so you can say then that negative 2x has to equal
3/4.
3/4 times x plus 3.
Okay, that's this one.
And now you just solve for x like usual.
Why did I think it's 3/4?
Because the second time it just makes more sense.
Okay. Let's bang it.
Now, your choice. You want to keep the fractions, you want to get rid of the fractions?
Get rid of fractions.
Get rid of the fractions? Okay. Okay, and so then the beauty over here is I'm just left with 3x plus 9. And I'm going to add over here, so that means I have 11x equals negative 9, and x is negative 9, 11. Ta-da! The 4 from this 4? I want to get rid of the fractions. I mean, you could have worked it with the fractions, but you like making common denominators more than I do.
Yeah, I got you now.
So, the key thing is make same bases. You have to have the same base number from the start. That's the key. First step. Make the same bases.
So if we have no way to make the same basis, like if that had been 28 or something.
Thank you, Gabriella. So, she's saying, yeah, what if I gave you 3 to the x equals 28, and you can't possibly make them be the same base? That's why we need logarithms.
Oh, yeah, okay.
That's, when we can't, that's coming, yeah. That's why you can't solve that. That's not possible without logarithms. So, one page? So, we'll do that. All right, last part. Do we all remember our friend E?
But so wait, today's only going to be ones that we can solve.
Yes, today is the only one you can solve. Today's will work. We'll get to how you do it when they don't work. Actually, not till next week. You're close. It's not Euclid. Euclid's the Greek. He's geometry. But not pronounced Euler, pronounced Euler. I did spell it. Okay. Okay, yes. Euler, probably one of the top 3 most famous mathematicians ever. Okay. Okay. Euler, okay, take your set, middle 1600s, no TV, no Facebook, no text messaging.
I know, you gotta drink a lot.
No, you do math for fun.
Hey, I know what you do on some of these. Some of these you gotta like put the I and cross the E off.
Not the I, the log in, but yes. Okay, that was the formula he was actually playing with. And he kept making,
It's your boy
n get larger and larger. So, for example, he would put 1 in for n, and if he put 1 in, he got 2 points, or he got 2, sorry. If he put 2 in for n, 1 plus a half, he got 2.25.
So was they out of booze at this time?
He thought this was interesting, thank you very much. Okay. Okay. You'll notice as he puts bigger and bigger numbers in, it's going up. But is it going up by the same amount every time? It went up, it keeps going up smaller and smaller amounts.
So it's like the graph.
So eventually if you put really big numbers in there,
It's gonna get really small.
it hardly changes at all, and in fact, it becomes the value, well, rounded off, 2.718. It actually is like pi. It goes forever.
Never.
But the value we use is 2.718. On your calculators, you have e, you have an e to the x key. I'll go back in a second. So if you're on your calculators, and just give me a scratch pad. If you hit your e to the x key, whoops, that was wrong. I didn't want that. I should hit shift. You hit, whoa.
That would be pretty day.
That was pretty cool. Okay. If you want to know e to the first power, e to the first power is 2.718.
That's a lie. It's supposed to be 1, bro.
Well, this only should display so many decimals. It does. Oh my heavens. Probably, yeah. Does it overflow? Shoot, even e to the 10th is e to the 100th. He says overflows.
Well, if you did too many, no,
Oh.
I did put E and E together.
Oh, okay. Well, okay, fine. There's e to the 10,000 overflow. Complete one. Oh, okay, fine. Seriously?
It overflows at 10,000.
It overflows at 10,000.
100 doesn't overflow any faster. It doesn't overflow either.
Times 10 to the 43rd power.
Oh, yeah.
Okay. It gets pretty big. Okay, now, does anybody remember why we care about E?
It's the nature number.
E is the nature number.
It's the same as LN, right?
It's the inverse, so that's the log inverse of it. We use it. It's coming, yes. Okay. It's the nature number. They found when they studied how fast plants grow over time, oftentimes they were growing to the base of E. A little bit bigger. How radioactive elements decay over time, base E. Some bacteria multiplies based on a base of E. E just kept showing up in things involving natural occurring events. So E became extremely useful to us. I didn't give myself a yellow. So you will notice on this paper are some formulas. We will be using these formulas on and off throughout this chapter. you'll notice some of them have a E in them.
Boo.
Okay, continuously compounded interest, which I personally think is silly, because no one would ever compound their interest continuously. That's why I fail to understand, other than it's mathematically cool, why I care about that one. So, I won't see me do much with that one, because I don't think it's real world value. But these two down at the bottom, notice one called natural growth. If you have something in nature, plants, bacteria, anything that's naturally occurring, that's the formula we apply to it.
You're going to use these three to test, right?
Yes, you'll have the sheet in test. And then a new one we'll be doing later on, not for a couple days. You haven't done before, Newton's law of cooling. It tells you how fast something will cool off. It's also the formula the CSI people use to figure out how long a body has been dead. It's Newton's law of cooling that lets them figure this out. So, okay, so you're going to want to keep this handy.
So you're saying I can create an algorithm. I can feel it. It figures out how much product I'm going to have.
Okay, I need to remind you about a special case with the business growth formula, the second one. Okay. You're going to discover on every single one of these formulas, what's on the left side of the equal sign is always the final amount every time.
Final amount on the
Okay.
left side.
Always. And the first number on the right side, the first thing being multiplied, is always your initial amount, how much you're starting with. Every single formula is going to be the same. That's B to the T. My T's here. Okay. Now, on this formula, the thing you guys have to remember is how to put the base number in. The base is how much something is growing or losing value. Not a problem we're going to do with these. We may just invent one. Okay, we're inventing one. What do y'all want to own?
Money.
I love pens.
Hey.
Tanks. Okay.
Jet flag.
You have an old World War II tank. Its current worth 22 million? Not that much. It's not worth 22 million. 22,000 maybe. Okay, it's increasing in value. At 5.2% per year. Okay, so it's gaining value at 5.2% per year. I want to know how much will it be worth in how many years? Pick how many years.
Oh, these are not thoughts.
So, oops, I just ran it off the screen there. Okay. If you'll notice on your sheet, it tells you the base has to be calculated from 100%. Okay, so since ours is gaining, you're going to go 100% plus the 5.2%, which means you're actually at 105.2%. You have to write that as a decimal, though, so when you put it in your formula, yes, it'll be 1.052. If it was losing at 5.2%, it was losing value, you would have to subtract 5.2 from 100%, which would leave you at 94.8%. But you always have to calculate it from 100%. Okay, now, what goes in the initial amount? The 22,000. Okay, and then what's your time? 20 years. Okay, and then you're gonna go to your calculator and just punch it all in.
Okay, where'd you get it? Okay.
But you need to use the exponential, you're using this formula. So, what's it come out? It'll come out similar, but not quite the same. 3.9.
I just got points.
You just got what?
No, I didn't get anything after 637. It's on
Which
slow.
formula did you use? Are you using this formula? You don't have to do this formula?
You don't have to check for a number decimal point, so it'll like stop without like.
Oh, okay. Okay. You're gonna, yes. Okay. Okay, now, here's the kicker question that's gonna happen to you on some of these. And I'm out of space. I'm coming over here now. Am I? No! No, I have one little piece to do. Rats.